Hello everyone. Today we will be discussing about pumping lemma for regular expression. Lemma means a theorem. To pump means that you push the input data and there exists such a path where one of the input character or string of character allows to pump part of word again and again. Please remember, showing pumping lemma holds does not mean regularity. This theorem is used to show that a given language is not regular. Now we say that pumping lemma is linked to pigeonhole principle. So what is this pigeonhole principle? The pigeonhole principle says that if you have fewer pigeonholes than pigeons and you put every pigeon in a pigeonhole, then there must be at least one pigeonhole with more than one pigeons. Say for example, we have 10 pigeonholes and 12 pigeons. It is probable that one pigeonhole may contain two pigeons or two pigeonholes may have one pigeon each since we had 12 pigeons. So we don't know which pigeonhole has how many pigeons. If we talk about the same thing in theory of computations, here pumping lemma states that all sufficiently long strings have a substring that can be repeated arbitrarily many times. And we don't know how many times that particular substring has been repeated. So this is how pumping lemma is related to pigeonhole principle. Now let's try to understand pumping lemma. Say for example, we have an automata for A, B, A. In this automata, length of the string which is accepted is 3 and number of states are 4, Q0, Q1, Q2 and Qf. Now let's consider automata for A, B, B star A. In this case, length of the string which is accepted is 3 or more, number of states are 4. But in this case, we can have a string of length n where n can vary from 0 up to infinity. ABA is accepted, A triple BA is accepted, A7 BA is accepted, A25 BA is accepted and so on. Can we know whether AB25 A was pumped or AB50 A was pumped? No, we cannot know. Machine cannot remember the count of number of iterations along the loop. That means how many times B was pumped in state Q2 cannot be counted. Now, can we say that this particular language is regular? Yes. Here, the range of B is from 0 to infinity. We have B star. We are not concerned about the count. Can we design A and Pn on similar lines? No, because when machines start iterating the loop of B, it cannot remember the number of times the loop of A has been iterated. That is, count cannot be maintained. Now take an example of A and Bn. This requires that number of A and B are equal. That is, if number of A is 3, number of B is also 3. We can remember them if n is defined, that is if n is 4, we can design a machine for A4, B4. Likewise, we can design a machine for A100, B100, but we cannot design a machine for any arbitrary value of n. How do we prove that A and Bn is not regular? This can be proved through pumping lemma. Now, what are the important conditions for pumping lemma? A language L satisfies the pumping lemma conditions if there exists an integer n greater than 0 such that for all strings W in L of length at least n, there exists x, y, z such that W is equal to x, y, z. Length of x, y is always less than n. That is, y is contained within n characters of W. And y is always greater than equal to 1. That means y cannot be epsilon. X and z can be epsilon. For all I greater than equal to 0, x, y, I, z is in L. So that means we can summarize this as every sufficiently long string in L can be broken into 3 parts where number of repetitions of middle part yield another string in. We can say that this middle string is pumped, hence the term pumping lemma has been used. Let P be any number, that is the pumping lemma. Find a representative string W of L of size greater than equal to P. Try all ways to break the string into XYZ triplet, satisfying the condition that y is greater than 0 and length of xy is always less than equal to n. For every triplet, show that for some I, the string XYIZ is not in L and hence it yields contradiction with pumping lemma. So this is how we will prove. To prove L is equal to A and Bn is not regular, let's consider W is AP, BP. We will divide this entire string into 3 parts. W is equal to XYZ such that XY is less than equal to P and Y is greater than equal to 1. So we will try varying options for Y. In the first case, we are assuming that xy is within AP, that is y consists of A only. Since w is equal to xyiz, the ultimate string which we have is 3a followed by aa with the superscript of I and 5b. For I equal to 1, w is triple a double a to the power 1 and 5b, that is a5 b5. For I equal to 2, w is triple a followed by 4 a's followed by 5 b's, that means a7 b5, which is not equivalent to a5 b5. That's a contradiction. Now let's consider second case. Here we are assuming that x is 5 and a consists of y only, b consists of z only. Now again, taking into consideration w is equal to xyiz, w is equal to a to the power 5I because y is I by 5b. For I equal to 1, w is a5 b5, very much part of the language as expected. Number of a and number of b are same. For I equal to 2, now we get a10 b5, which is not part of the language. Number of a is not equal to number of b. So this is a contradiction. Hence the above cases prove that a and bn is not regular. We take third case where xy overlap between AP and BP. That is, y consists of A and B. Since W is x, y, I, z, we are putting it 4a followed by ab to the power I and 4b since 1b has been represented by y. For I equal to 1, we get a5, b5, very much part of the language. For I equal to 2, what is the output which we get? It is a5b a b5, which is not equivalent to a5 b5. Now the most important point which needs to be considered here is that this case cannot be considered since the condition that xy should be less than equal to p is not satisfied. What is the value of xy over here? Xy in total comes out to be 6, whereas it should be less than equal to p, which is 5. Same is the case with this case. If we consider that y is part of b, again the same point will come up that first there is a contradiction, that is fine, but otherwise this case cannot be considered since length of xy should always be less than n. This is one of the preconditions to prove that the language is not regular. Now, many a times you'll come across the cases in many of the books where we will have, instead of some specific value of n, we will have n is equal to k. In order to consider those cases, I have drawn one slide for that also. Just consider that x is a to the power n minus k. That means y is k because total should be a and bn. Now, if x is a to the power n minus k, y is k, z is b to the power n. We will consider the same things, that is w is equal to x, y, I, z. So that means a to the power n minus k, a to the power k to the power I and b to the power n. When we take k is equal to 1, we get w is equal to a to the power n minus k into ak into b to the power n, which is equivalent to a n bn. K n minus k plus k is an. Now we move to case k is equal to 2. In this case, we have value of y is ak to the power 2, which is ak into ak. That means k plus k. So this is coming out to be a to the power n plus k bn. Since this is not equivalent to a and bn, we say that a and bn is not regular. This is a contradiction. So this slide has been specifically used in order to clear it that if we take value of n equal to k or we take any specific value, we will always land up with the situation that a and bn is not regular. So we can summarize this as that we have discussed pumping lemma for regular expressions, which is used to prove that a particular language is regular or not. In the coming slides, we will discuss the second phase of theory of computations, that is context-free grammar. Thanks for watching.